Hi, welcome back my statics friends. In this video, we're going to continue our discussion of some basic vector operations. In the last video, we were talking about things like vector resultants, vector addition, and some of the basic properties and characteristics of vectors and what they can do for us. Today, we're going to actually get into some example problems, and we're going to kind of start setting up some basic properties and identities to kind of show you the methodology of what it is that we're trying to do. Okay, so without further ado, let's get started. So in this lesson, we're going to be talking about kind of the parallelogram law and some basic triangle construction techniques that can happen with the methodology that we're dealing with. In the last video, we were talking about things like vector addition, and we had this basic equation that said an R vector was equal to an A plus a B type of vector on this thing. Okay, and we define that as, if this is my start point and this is my end point, that we could construct a path that goes from the start to the end by following a vector A and then a vector B to get to here. Or I could do the opposite side where I went B first, A first, and I ended up at the exact same point. The R vector that connects those 2 points is the same. It has the same distance and it has the same direction and sense of the line of action on this thing. Okay, and so the methodology that we kind of look at is kind of, well, if I can define A and B, then finding R is pretty easy to do. Okay, and this was basically the picture that represented vector addition. Okay, now vector subtraction is a little bit different. All we do on this is it's basically, since subtraction is the inverse of addition, is that I can say I have an R vector, or in this case an R prime vector, that is A vector minus B vector. So this is my A vector and this is my B. If I do my construction on this, A plus B would give me a resultant that went somewhere up this direction. Okay, but if I look at what we've done is I've taken an A vector and I've added a negative B vector to it. Okay, and basically what happens is you flip the direction of the B. So, and then it's just a simple addition like what we did up above. And so if this is my common point and my A vector remains unchanged, then I flip B, so instead of being to the right here, it's now to the left. Then I can construct this exactly the same way, that the R prime vector that connects A and negative B would be the guy that cuts across the middle of this basic shape. Now again, this is kind of outlining our parallelogram law where we have parallel sides of this object and that the R connects the opposite diagonals of that particular shape. Now, in all of these cases, what you notice is whether you're doing a subtraction case or I'm doing the addition case, I'm basically creating triangles on this. Okay, and this becomes the key to being able to compute some properties for, dimensions and angles associated with standard triangles. And to do that, we have a couple of laws that are pretty common, and these are worth memorizing if you don't already have them. Okay, and so there's a lot of different versions of the law of cosines and the law of sines. The law of sines is pretty simple. It says that for a triangle consisting of sides capital A, capital B, and capital C with angles of little a, little b, and little c. Now notice capital A is across from angle little a, capital C is across from angle little c, and capital B is across from angle little b, that basically the ratio of this side to the sine of that angle is constant for all sides of the triangle. It's the only way mathematically that it works. Now we're not going to get into why that's the case. We're just going to take it as that's the case. All right, so A over sine A, little a is equal to B over sine little b is equal to C over sine little c. And so what you can see is that if I follow the law of sines, if I know any three of these and I know one of the ratios, I can find the other one. Okay, so say I know A and sine of little a, and I know the length of B, I can find this guy. Or maybe I know the angle, but I don't know the magnitude. I can find it using the law of sines. Very, very powerful stuff. Okay, now, the law of cosines, one form that you might see is that C is equal to the square root of A squared plus B squared minus 2AB cosine C. Okay, well, what that says is that the side distance of side C is equal to the side of A squared plus the side of B squared minus 2 times the side of A times the side of B times the cosine of the angle little c. Well, if this is A and this is B, the angle that I'm using is called the included angle. It's the one that is in between A and B. So that's that little c guy. Now there are different forms of this law of cosines, right? I could say that, A squared is going to be equal to B squared plus C squared minus 2 BC times the cosine of what would then be little a. Or you could rearrange this again. B squared is A squared plus C squared is 2AC times the cosine of little b. All of those are valid versions of it. Now the thing that's kind of cool about this is take a look at this basic equation. Let's say that, angle A is 90 degrees. It's a right triangle where I have, a vector on the bottom, a vector on the side. This would be the resultant that connects those two, right? Well, if cosine of 90 we know is 0, this term goes away. And if I cover that up, look what pops out. A squared equals B squared plus C squared. There's Pythagorean's theorem hiding for you right there. Okay, so this is a more general version of Pythagorean's theorem. Okay, it's just Pythagorean theorem is one specific case that it had to be a right angle. Now I'm saying that that's no longer a requirement. If I do the whole equation, I can now plug in whatever my angle is here, and we can actually start to solve for things. And this becomes the key to finding the resultants and their directions. Okay, these two laws in general will help us to kind of set ourselves up here. All right, so one of the things that we can do in this construction is we can look at something known as the triangle rule. So all I've done is I've drawn kind of a simple triangle construction. And again, we're going to do lots of stuff with A's and B's and doing different tricks on this. And so all I'm going to do is I'm going to take a line of action of A, okay, which is this line here, and you can see I've labeled line of action of A here. Okay, and then perpendicular to that line through the endpoint of this, I'm going to draw another line. Okay, and it's going to be perpendicular to what would happen with my A. So that's 90 degrees right there. Okay, and so what we can do is we can start kind of playing this component game whereby, let's say that, from here to here was my vector A along the line. I can construct a piece from here to here that is some amount x. Okay, and it's based on whatever this angle is of where B is in relation to A. Okay, and then y would then be the distance from this point to this point along this line. Okay, and again, it's related to that angle, whatever it happens to be. Okay, so if we look at this, that that if what would be my angle, we're going to call this as alpha here. This little guy is alpha of B relative to A, and theta is of A relative to R, or the orientation of the resultant on this thing. Well, we can come up with some basic properties using basic trigonometry, because again, this is a right triangle, that the distance B, this would be the hypotenuse of that right triangle, that the B times the cosine of alpha would be that quantity x. And then y is equal to that B times the sine of the angle alpha, that is this angle right here. Okay, and so what we can do is, you can always, if I know the angle alpha, that we can always compute the quantity of this A vector, the magnitude of A, okay, plus that x quantity. That gets me the distance from here to here. Whoops, pull that down, sorry, a little bit. That gets me the distance from my start point to this common point where these two lines cross. Okay, and again, these are perpendicular, these are 90 degrees to each other. That gets me this quantity. And then if I know those two pieces, and you should know, if you know A and B and that angle, which you should know that, okay, then I can find what would be x and I can find y. Well, we can then find the resultant of this by simply calling this big triangle here, taking the base of the triangle, which was A plus x, and squaring that quantity and adding to it this y equation. And so I can do it that way. It looks like that, and if I take the square root, that's the, and I have squared here, that shouldn't be a squared. Okay, but the magnitude of my resultant r then is A plus x quantity squared plus y squared is one technique for being able to do this. Okay, and once I have that, then I can find the angle theta by just doing simple trig of my dimension y divided by A plus x. Okay, or this. And now you've got a tool, very simply, to be able to come up with the resultant as well as the angle of that resultant. Okay, and again, that's the angle measured from the line of action of this A vector, or my basis vector. And if I know where this line is, then I can fully define where R is. And now I've got everything. I've got the magnitude of R, and I have his direction, and I have his sense tracked out that way. And so that's a pretty cool way of being able to do stuff. So that's our triangle rule. Okay, all right. Now, let's go take a look at a slightly different construction technique. Make sure I get the right page here. Okay. Okay. And it kind of ties into this triangle rule, kind of ties in a little bit to what we're going to call as the parallelogram law. So what I have is I have a small object happening here that has two forces on it. I know that I have a force that I'm going to call as F2 that is 150 newtons, and it's measured at 10 degrees off of a vertical line going through the center of the ring. So this is like a tie-down ring with two ropes pulling on it in given directions. Okay, and then I have a vector F3 that is 100 newtons that is measured 15 degrees off of the horizontal. We want to find the magnitude and direction of this resultant. Okay, now the parallelogram law, if we construct this, there are several things that we know about parallelograms. Okay, the first one is that for any parallelogram, it has to have parallel sides. So the first thing we do is we do parallel sides. If we start to kind of look at that. So that's our first one. Next property that we know that opposite sides are equal in magnitude. Okay, as well as opposite angles are equal. All right. So if we look at basically a quick parallelogram shape that looks something kind of like this, if this is this side and this side have to be equal, of course my line's a little bit off. All right, I know that this side and this side have to be equal. I know that if this is an angle alpha, then this guy here is also an alpha. And if I know that this is a beta, then this guy here is a beta. Okay, and so those are all properties of a parallelogram. The other one that we have, which will be my fourth property, is that 2 times alpha plus 2 times beta has to be equal to 360 degrees. All right, we know there's 360 degrees in a square. The square is a parallelogram, and that's 2 times each of the angles will get us to that. All right, so 2 times alpha, so alpha plus beta, that's what that formula says, that's equal to 360. So if I know some of these lines and I can figure out one of these angles, then I can start to work out what the other angles are for what we're working on here. Okay, all right, so if we look at this, then we know that if I draw my picture on this, and here, and I'm going to zoom this in a little bit, see if we can look something kind of like that. And I apologize, the camera's a little blurry today, but I think we'll be able to get through. Whoa, refocus. Not a whole lot better. Let's see. Tighten that. All right. Yeah, it's just not real good. I'm zoomed in a little too far here. Sorry about this. Pull it out a little bit. Probably a little bit better. Okay. So what we do is we basically draw our coordinates. So I'm going to draw my horizontal references on this. So here's my reference. 15 degrees goes from this horizontal up to my 100 Newton force. And it's 15 degrees from my vertical over to my 150 Newton force. So I know then that the angle between these two vectors is going to be 90, because it's 90 between the reference lines, minus 10 minus 15. So that should be 65 degrees. That's the first calculation that we do. So this angle from here to here is 65 degrees. Well, if I look, I can call that as alpha, 65 degrees, which means the one on the opposite end is 65 degrees. So if this is 65 and this is 65, and the total of all of these added together is 360, I can solve for what this other angle is here. This is what would be my beta angle on this guy. So all I'm doing is I'm taking 360 minus 2 times alpha of 65 and dividing by 2. It's just simply rearranging this formula and solving for beta. Beta equals out of that equation. That's all I did here. And so I can find out that this angle is now 115 degrees. Okay, so now what we can do is we can draw one of the triangle resultants of this thing. Okay, and just basically it doesn't matter, you know, I've got two paths, and again, we said vectors don't care which path you take. I could go up and then over, or I could go over then up. Doesn't matter. It's still the same R connecting them. So for this example, I chose to take the lower bound path. Okay, and so I know that based on my triangle, that I'm going to go from a start point that's right here. I'm going to project 100 newtons this direction. Okay, and then from this point, I'm going to go up 150 newtons, and the angle between those two is that 115 that I found. All right, so if this is 115 here, okay, then I've got everything I need based on my law of sines and law of cosines to be able to solve for this FR, this resultant force value. Okay, so we know two sides and the included angle. This tells me that I can use the law of cosines then to find FR. So if we plug in to that formula, that basically said you take the squares of both of the sides. Okay, so that's 100 newtons squared plus 150 newtons squared minus 2 times 100 newtons times 150 newtons, okay, times the cosine of the angle between them is cosine of 115 degrees. Now, friendly reminder in this class, when you're doing this formula, make sure that this guy is in degrees. Okay, I know when you're taking Calc 1 or Calc 2 or physics, a lot of times you'll work things in radians. That will make a drastically different answer to your calculator. So always check for this class, you need to be in degrees, almost always. Okay, all right, so then cosine of 115 degrees, if I do the math on this by punching it into my calculator, I get that it's a 213 Newton force. Okay, so it's 213 newtons to get from here to connect those 2 points. Okay, now, the one thing that I don't know, I know his magnitude, but I don't know his direction. All right, so we're going to find my angle theta then on this, okay, by taking and using the law of sines. I could use the triangle rule, but I can also use the law of sines on this, and that's what I'm going to choose to do on this case. And that basically said that the opposite side in an angle has to be, and the sine of the angle have to be constant. So I'm going to take, you know, since I want theta, I need to make sure theta is one of those, so I need to take the side that's opposite of this, which is the 150. So 150 to sine of theta is going to be equal to 213, which was my FR value, and its opposite angle of 115 degrees. Okay, and when I do that, and you do the math and solve for theta, you can find out that theta is now 39.8 degrees. All right, so the final picture, the final answer of this thing, okay, is that now theta, remember we said, was measured from the line of action of this first vector. It's theta from here up to here. Okay, normally we represent that relative to some reference, which a lot of times is the horizontal x-axis, x where horizontal is 0. So if this is my horizontal axis, then I know to get from horizontal up to A, we said that was 15 degrees. Okay, and then to get from A up to my R would be another 39.8. So if we draw our picture, then 15 plus theta is 15 plus 39.8. That's 54.8 degrees. Okay, and I always draw kind of this arrow to tell me that where I'm measuring from. Because if you just told me it was 54.8 degrees, the first question I would ask you is, measured from where? Okay, so I need a picture. You can measure it off the vertical, you can measure it off the horizontal, it doesn't matter, but I got to know where you're measuring from so that we're all on the same page. Okay, and I'll, you know, on a quiz or an exam, I will accept either answer as long as it's the right numerical value. Okay, because I'm not going to penalize you for choosing the wrong reference on this. Okay, but for us, then I'm going to say that it's 54.8 degrees measured from the horizontal. So these two pieces define the vector. Okay, that I measured 54.8 degrees from the vector. The tail of the vector has to be here, and I have to draw my arrowhead on there to indicate that it's starting here and going up that direction. Okay, and then it's 213 newtons along there. So these two pieces represent the solution to that answer as we start to look on that. Okay, all right. So that's kind of a quick run through of the parallelogram method as well as kind of the triangle law breakdown. It's very simple mathematics. A little bit of trigonometry in there, but nothing you can't handle. You know, you got your SOHCAHTOA. You know, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. All rules that you guys should know. Okay, and then with that, I can do a whole lot of things just by playing with these construction techniques to be able to solve for the parts and solve for the angles that you know. Parallelogram law will go a good ways towards being able to find a resultant of two forces Which brings us to the first problem that we're going to have in this particular class. What do you do with an object that has more than two forces? Well, you have to tune in next time, and we'll talk about it then. So, as always, if you found the video useful, please toss us a like or subscribe, and we will see you guys next time. Have a great afternoon. Happy engineering.